Hi, everybody. Welcome back to this last episode of this season 6 of the Latin American webinars on physics, law physics. So today is a very nice webinar because it's going to be about one of the topics that I am most enthusiastic, that is dark matter. So before to go directly to the webinar, first remember that if you are watching this via YouTube or you get news about Facebook or whatever, you can give a like to our Facebook page, to follow us in Twitter, and also to subscribe to YouTube. So now the speaker of this webinar is going to be Daniel Coderre from the University of Freiburg. He's postdoc there, and he did his PhD in the University Bochum in Germany, I guess. Mm-hmm. So Daniel, if you are ready, you can start with your. And welcome to this webinar, and thank you for present the results of the XENON experiment.
All right, thanks for the introduction. So go ahead and share slide deck I have here. Great. All right, and if for some reason something stops coming through, just let me know. But so here we see already a very nice picture of the subject of the talk. This is about the XENON 1-ton dark matter search. And this is our beautiful detector and support systems sitting underground at Gran Sasso in Italy. So I'm going to talk about this running system mostly and our plans for upgrading it coming. So our collaboration, to get an idea of the size, I'm representing about 20 institutes or more now. And now we've grown to about 160 people. So that's for the XENONnT stage. We're about 130 for XENON 1-ton. So it's a medium to large collaboration and made up of institutes all around the world. So it's getting harder and harder to find a good time to have a meeting. So this is an experimental talk. So you only get one slide on dark matter. But I've seen your webinar series. I think if people are following, they are a little more familiar with the subject. So the point of this, so we're looking for dark matter. There's evidence that dark matter exists. It's pretty convincing. I think every physicist would say they're at least more or less certain dark matter is a component of the universe. And we see this on a lot of different distance scales via missing mass. So on the galactic scale, we have galaxy rotation curves. We need dark matter to explain. The extragalactic scale, we have moving, so dynamics of galaxy clusters, which we also need dark matter to explain in galactic collisions. And on the universal scale, we have these very famous Planck measurements where we see through the CMB that we need quite some mass in order to make the observations match our theory of how the universe developed. And XENON 1-ton is searching for not just WIMPs, several other models of dark matter too, but the main search we do is for WIMPs. This is a very general form of dark matter. Comes out of a lot of theories, and what we're basically looking for is weakly interacting massive particles. So weak scale interaction, no electromagnetic interaction, so suppressed interactions with normal matter. Masses, you have to have mass, so WIMPs can go MeV to TeV. For XENON, we go from a few GeV, so 10 GeV or so, to TeV for our main search. We also have other searches that try to go to lower masses. An important thing about WIMPs is they have an energy density, so put 0.3 GeV per meter squared. This is rough, but that means in our sector of the Milky Way, every square meter of space has some WIMPs in it, and we're flying through them. Or seen from our perspective, they're flying through us. So you can make a Earth-based detector, and you make your detector out of some material, and there's always a flux of WIMPs going through it. This is a principle of Earth-based detection. And you're thinking about what material to make your detector out of. We picked liquid xenon. Liquid xenon is actually a great material for making a WIMP detector for a lot of reasons. So first of all, when you're looking for a WIMP coupling to matter, you can either have a spin-independent or spin-dependent coupling. The spin-independent coupling is experimentally easier because it's proportional to the atomic mass of your target. And xenon is a big atom, so it's 131 atomic mass. And this means that we're looking for a relatively strong coupling. This makes also a very nice, so what we're looking for is coupling to the nucleus. We get a nice recoil spectrum from xenon, so this is shown here. So you might think of using some other elements like argon, germanium, and other detectors do. Xenon has a very nice recoil spectrum. You see an enhancement here at low energies, for 100 GeV WIMP. So if you can measure energies around 20 keV or so, you get a high statistics in nuclear recoils. Relatively high statistics. This is, of course, a very suppressed or non-existing interaction. Another thing is when you're looking for dark matter, the only real way to do it is to close out every other known interaction. So you have nothing left, and whatever you have left, you have to understand. So we need a low background environment, and xenon can be purified a lot. It's a noble gas. So we hit very high purities, and except for XENON-136, which is interesting in its own right, there's no radioactive isotope in xenon. Its density also means that it shields radiation. So the inner layers of xenon are even more clean than the outer layers, you can see from the background standpoint. And a big thing when you're thinking of building a detector, you have to actually build it. So it has to be possible to make. So liquid xenon is nice because it's heavy, and you can also put it in a bucket, right? So it's liquid at a temperature higher than liquid nitrogen temperature. So this opens up all opportunities in the lab. You don't need some helium cooling or something. And it's a scintillator. So it's actually simultaneously the target and the particle detector because it scintillates light. And we'll talk about that in a minute. And for a lot of these reasons, so liquid xenon TPCs have kind of taken off in sensitivity towards between WIMPs and matter. That's shown here. So this is a plot from our first paper from XENON 1-ton, our first result paper from last May, and now we're going to talk about the new one, the update. So XENON is a stage project because when you want to build a sensitive dark matter detector, you don't get around building a bigger one. There's all kinds of other considerations. You have to always make it more and more radio pure. You always have to solve a lot of practical problems when scaling up, but in the end, you need the mass. And so I kind of drew a cartoon here where you see the target mass. It's a mass inside the TPC scaling up from XENON 10, which was like a thermos, XENON 100 trash can size, maybe like a short one. XENON 1-ton is already like a big barrel. So it's 1 meter diameter, 1 meter drift length. This is already a large thing and 2 tons of xenon inside. And I'm going to mention here, I guess for the last time until the end, our upgrade, which is already under construction. So XENON 1-ton, the picture is here. It's running right now. XENON-n-ton, so this is XENON-n-ton because we didn't know how many tons we were going to make it when we started. We just knew it was going to be bigger. That will have a total of 7.5 tons of liquid xenon, which we already have stockpiled, 6 tons inside the detector in the active volume, and that'll be about 1.5 years from now. We'll start operating it. And you can see here the outer cryostat here is actually the same outer cryostat as XENON 1-ton. We made it extra big so it will accommodate now this bigger inner cryostat. We can just upgrade it in place. So we can be really quick with getting the next stage out, which is important because this is a competitive field right now. So here's a nice shot of our bottom photomultipliers during installation. I'll talk about how we actually detect dark matter with this TPC. With liquid xenon TPCs in general, there's a few of them out there, all kind of competing for the top spot. But we're going to have it. Good. So this diagram here shows how liquid xenon detect TPC works. So it's one detector, but 2 stages, basically. On the left, it's just a scintillator, right? So you have a particle coming in, and it makes scintillation light, as we said, 178 nanometers in the liquid bulk. And this is seen by 2 arrays of photosensors here on the top and on the bottom. And that's it. So very normal detector, you're familiar with if you do any type of experimental physics, scintillation light collected on each end. And then you get, here on the bottom, we have a kind of waveform. So you get then this pulse right when the particle hits. The second part is kind of the tricky part for liquid xenon detectors, and this is where we get our second signal, which is ionization. So the second energy loss channel for particles hitting liquid xenon, that's ionization. They create free electrons. If you don't do anything, they just kind of sit there and recombine eventually, but we put the entire volume under an electric field. So down here is a cathode grid on the bottom. Up at the top is a gate. So this is, we call it the gate. It's another electrode. It's at 0 volts, so we have then an electric field between the 2 of them, and it causes the electrons to drift up towards the gate. And here's something a little tricky happens. So above the gate, we have the liquid stops, and we start with gaseous xenon filling the rest of the volume. The liquid gas interface is right in between the gate and the anode. The anode is biased at 4 kilovolts, so quite close together, and there's a really strong local electric field. And this causes the electrons to be extracted into the gas where they make proportional scintillation light, so they're amplified. Or, sorry, proportional amplification. So they're amplified then in the gas phase. What you get here is a localized signal in XY. So you see kind of in the cartoon here, you know where the interaction happened in XY, assuming they drifted straight up. The time difference gives you the depth, and so you get 3D reconstruction. Then you have the energy loss from both channels. And one more trick we have up our sleeve, we want to know when a WIMP hits a nucleus. So WIMP shouldn't hit an electron. As we said, the coupling is, they're electrically, don't see the electromagnetic force. They shouldn't couple to electrons in any measurable way. So most of our background, though, is electromagnetic. So we're looking for nuclear recoils, and we want to filter out recoils against the electrons, electronic recoils. That's shown here. So electronic recoils are shown in blue, where we plot the S2 signal versus the S1 signal. And then in red is nuclear recoils, and you see that we can separate them. This is becoming very important later for the analysis. Here's what it looks like in real life. So this is a waveform where you have the S1 signal, nice tight, see 0.4 microseconds here, so microsecond time, sub-microsecond time, it's light. Here you have the S2 signal blown up here. Here you see several microseconds, wider, and there's this localized signal. This is the top PNT array. It's just a heat map, the area in each channel. You see what the interaction happened already by eye, and the drift tells you about how deep it was. This was about a third of the way down the TPC. Good. So if you put the detector underground, you measure kind of nothing except your backgrounds. And if we want to understand our low energy background or low energy signal, we have to calibrate. We calibrate in basically 3 ways. So the first way, we need to look at our low energy electronic recoil backgrounds. We need electronic recoil events. And this is a little counterintuitive. We have this nice detector we spent a long time building and a long time making radio pure so that there's no radioactive background in it. And then we pump a radioactive source inside. But radon 220 is kind of nice radon, so everything here is very short-lived. The longest is this 10-hour half-life. So you can always wait 3 days, 4 days after pumping it in, and you're back to background conditions. So we do that. We pump this radon 220 in, and we get these beta decays from lead-212 that give us low-energy electronic recoils very nicely. So we measure every month or 2 the response of our detector to that, make sure it's stable, and we use this later in training our analysis to know what the background looks like. We use also Krypton 83M. This is another internal source we pump into the detector. It's also short-lived, 2 hours. We pump it in about every 2 to 3 weeks, and this gives very nice 2 lines, a 9 and a 32 keV line, about 150 nanoseconds apart. So sometimes you see them as 1 reaction, sometimes it's 2, depending on how long they live. And this is homogeneous in XYZ. So we wait a little bit after pumping it in. It gets mixed around by the flow inside, and you have just this homogeneous source of known energy. We use this for a lot of calibrations we'll talk about later. And the last thing is neutrons for signal response. So neutrons look like a WIMP in our detector. We're looking for nuclear recoils. The neutrons make nuclear recoils. We've done a couple runs of Emirates and beryllium source. So you can see a diagram here. This is the TPC, and outside we have this little box that we can move up and down. Very simple mechanical thing, and you move it into place, and it creates signals in your detector right here. We also have a DD neutron generator. We also lower into place and can power, and the 2 days of that are about as good as several weeks of Emirates and beryllium, so we're happy to have this online now. We'll show the spectra from these later. Good. So when designing the detector, so there's a few, you have to kind of make it good at doing 2 things. So the S1 signal and the S2 signal. For the S1 signal, you were worried about your light collection efficiency. So you want to collect as much of the light from the original interaction as possible. So the particle comes in, light goes in every direction, and you want to collect it. The best would be if your whole detector was just made out of particle detectors. Practically, this hasn't been possible yet, so the next best thing is we pick something really shiny that reflects a lot of light, and we line our whole detector with that. We use Teflon, PTFE, for this. You can see here, looking from the bottom up, this is the top PNT array during construction, so this will be filled with liquid xenon later, and these are Teflon panels. Teflon's very good because it's you can get it pretty clean, it's not very radioactive, and you can polish it so that it's 95 or more % reflective. So there's a very high chance of reflecting an incident photon. Another thing is you need photomultipliers that have a good chance of detecting a single photon if one hits it. And for that, we use specially designed Hamamatsu PMTs. We have 248, about half on top, half on the bottom. They're designed to run in a liquid xenon with a high quantum efficiency, so 35% at our scintillation light. It's pretty good. High gain, so 5 million, factor of 5 million at our operating voltage. And we get acceptances of single photoelectrons of about 94% on average. So some better, some worse, and this depends on the electronics in the particular PMT, of course, but the average is about 94%, which is quite high. And for most of our channels, the gains are stable within 1 to 2%. This is a plot over the whole science run since we switched over to a new database, so it doesn't quite have all the data in it, but it shows that these are really quite stable over time. And the design is for low background, so it's minimizing material budget in every part of the PMT. And another thing is the electrodes, right? So we have these electrodes that have to span the whole TPC, so the light has to go through them. We design them to be as transparent as possible. I think the worst transparency is the anode, and that's already 90%. All the other electrodes are better. So you can see here, if your monitor is good, you can see the meshes here. If your monitor is not so good, then it might look like there's nothing there, and that's kind of the point, that you can see right through them. Good. So you see later in plots, if you're astute, corrected S1 signals. We do one correction on our S1 signals, and that's for light collection, depending on where the S1 happens in the bulk. So because of interactions at the liquid-gas interface, if a reaction happens in the bulk, we're more likely to see it in the bottom array in general than in the top array. So most of the light will be collected by the bottom array. And just because of solid angle, you have a higher efficiency if you're closer to the PMTs and closer to the middle. And you can see that in this plot here. This is the radius of an interaction. This is krypton 83M, fixed energy interaction, versus the depth. You see right in the middle bottom, we have the highest parent signal. And at the top corner, we have the lowest. This is well understood. We simulate it in Monte Carlo, and we measure it, and we correct the signals with this. Then we can monitor over time the stability of the light yield using radioactive sources. So radon 222, terrible background, but we also, it's useful in some ways. We use it for monitoring. Activated xenon, so neutron calibrations will make short-lived isotopes of xenon. You see that here. And krypton 83M, and we see it's flat for science run. So we say our light yield is high and stable. For the charge, it's a little different. There's a few more things you have to worry about. So first of all, if you have very perfectly pure xenon, which nobody has, your electrons will drift to the top, and you'll get all of them out at the top and start at the bottom. In reality, you have electronegative impurities in your xenon all the time that we're constantly filtering out, and they can absorb these electrons. And so we have to correct for the absorption. This is a function of the depth of the interaction, so how much xenon it had to travel through, drift time actually, and the purity. You can see that in this plot here. We call it electron lifetime because if you plot it, it looks like an exponential falling, and you can fit a slope and get the lifetime from this. So the electrons are stable, but it's the lifetime in the detector of them being absorbed as they drift. We see this rising throughout our science run. Basically, there are jumps. The jumps are some known disruptions, either an operational thing. Here, there's an operation where we intentionally change the liquid level to get dust off our anode. That's knocked a few impurities in, but then we recover right away. We see it slowly rising and plateauing, sort of hitting about the maximum purity for our current setup. We monitor this with radon alpha decays, radon daughter alpha decays, and a krypton again. We have a second correction for this for amplification. So our anode and gate, remember we use a strong field between the two of them to extract the electrons into the gas phase, and this is where you get this proportional amplification. These are not perfectly the same distance apart all the time, and they're not perfectly the same distance between the anode and the liquid level, because they have to span 1 meter, and they're very small. But we can correct for this, and so we see here the S2 correction. You can see there's a bit of sagging in the middle and a bit higher on the outside, but this is well understood. So when you see a corrected S2 signal later, we correct for these things. These are things we constantly have to think about when operating the detector. If we look at our charge yield over time, we see this is also quite stable with maybe a slight rise, which we're attributing to our increasing purity over time. And we monitor this also with the same sources that we use for the light yield. You get the energy now from this, right? So the S1 and S2, you've corrected them. You get the actual S1 and S2 energy at the interaction point. And then you can convert this to energy just very simply because you know that the particle had to lose energy either through light or charge. So the two are anti-correlated. So you could say the S1 signal is proportional to the of light quanta compared to total, times some constant you fit to the data. And the charge signal is the same thing times another constant, only with the proportional charge quanta of the electrons. And if you exploit this relationship, you can make a plot here with known radioactive sources of fixed energies that are inside the detector, and you see they lie along a line. And this is a good proof of this anti-correlation, that the light there, that the energy has to be lost through one of the two channels. It's called a dope plot. What you can also do is, so you take these two equations, you can solve them for energy. You get a function of energy as a function of S1, S2, and these constants you fit, and then you can make a nice energy spectrum, which we show here, where we see the gray boxes are blinded for various rare event searches. So radioactive peaks here from these are activated xenon. These are material background peaks. A big broad distribution from the 2 neutrino double beta decay of xenon-136. And we see this spectrum goes from 0 to 3 MeV, but actually our search matter for WIMPs, the most vanilla WIMPs, is down here. It's about the width of one of these ticks on the axis. So we're going to zoom into that later for the rest of the talk. And we get a very competitive resolution if we just fit the resolution we get from these peaks. So here's our resolution curve versus energy versus some of the other experiments. You see we're quite up there with the other TPCs and with ourselves from earlier. We've actually improved on our previous device. So one last thing is the S2 position. We won't spend too much time on this. So the S2 position is reconstructed with a neural network that we train with simulation. And then we correct various effects in the detector, like inhomogeneities in the drift field, inactive or misbehaving PMTs, give local problems. We correct those using an empirical correction from Krypton data. What we get here is background data looks like this. You see more activity at the edges. This is XY, RZ. So here's a detector wall, and then clean interior. And then external source will have a different distribution. Of course, it looks like this. This is neutrons coming in. You see that they're interacting mostly on the edge here. We still get quite a few in the internal volume. Good. So, very important point of this is backgrounds. So, for rare event search, you have to have your backgrounds down as low as possible. Electronic recoil backgrounds, so we said before, electronic recoils can be filtered out a bit later in the analysis. They're a bit less dangerous than nuclear recoils. So, talk about those first, and keep in mind we care a bit less about electronic recoil than nuclear recoil, but it's still important. So what we can see in this chart here is that most of the electronic recoil background comes with radon 222. And this isn't too wrong with radon 222, we just did a really good job at getting the other contributions down. So the material background is quite low. We get this low by screening every screw and piece of steel and piece of plastic that goes into the TPC with germanium detectors beforehand. And this is an example spectrum of this. Here we screen some high voltage connectors to make sure that they didn't accidentally put some radioactive impurities into our detector. And we have a very aggressive screening campaign where we really screen everything before building the detector out of that material. Krypton 85 is also low, and that might make you think it's not a big problem, but it's a really big problem for liquid xenon TPCs. So when you buy ultra pure xenon from the distributor, it comes with krypton in it. And it's not that much krypton, right? So it's about, so natural krypton levels are suppressed by a few orders of magnitude already, but krypton 85, the radioactive isotope, is suppressed now by 10 to the minus 12 compared to natural krypton. But we still care about it because it will create electronic recoils in our detector. So what we use is a dedicated distillation system. So we distill the krypton out of the xenon. Even during operation, we did this, and we see this here. So this is our background rate versus time. And here we see it kind of falling. So we're distilling the krypton out. That's these gray periods. Here it kind of flattens. Here we distill again, and it falls. And the red points are measurements using rare gas mass spectrometer of xenon taken out of the system. We see that as the krypton drops, eventually the background rate will flatten out, and here we're radon dominated. So for XENONnT, radon is going to be the big challenge. And we're going to try to distill this in a similar way out, so backwards, but using a similar system. And radon, you also have to just try to minimize by minimizing leaks and measuring emanation of your components and choosing components that don't emanate so much radon into the system. So that will be the challenge for NTON. Nuclear recoil backgrounds, so there aren't so many. So the first thing is muon-induced neutrons. We suppress that by putting the detector under a mountain. So you get a factor of 1 million less muons. And then we suppress it further by putting everything inside a water tank. So this attenuates all forms of radiation that might be coming towards the detector. And then we suppress it again by instrumenting that water tank as an active Trenkov muon veto, which has a high efficiency of tagging muons crossing it. So we expect very few events from this, 0.012 events per ton year. What we're worried about here is the neutrons that can come from a muon shower. Not the muon itself hits our detector. It doesn't look like dark matter. It looks like saturating every channel. The most dangerous background for this stage is radiogenic neutrons. These is a material background. There's not really anything you can do once they're in there. You have impurities in the material, so alpha N reactions that cause neutrons in your volume. This is a spectrum of what this might look like. You see the penetration is a lot more than the electronic recoils, but luckily this is scaled way up. If you scale it down to the level that we expect about 1 event per ton year, and we minimize this by minimizing the material budget and screening and selecting materials carefully. Good, and the last part, neutrino scattering. So this we don't see in XENON 1-ton, XENON-nT this will become an issue with solar neutrinos at lowest energies. So XENON-nT we start to get into this, into a region of the parameter space where we might see solar neutrinos. And this is irreducible, so they come, it's a background that comes and you can't tell it from a WIMP, so you just have to accept that that background will be there. Good, so there's a couple other sources of background here, so I'll go through a little quicker. One, so every time we run a xenon experiment, you find like a surprise one at the end. So I think this was the one from XENON 100. Accidental coincidences where you get low in S1 and S2 signals. This is low in S1 and S2s versus time. They can accidentally combine, and then you get fake events that look like signal. And we build an empirical model to handle these, expect less than 1 event in our search region from it. But we expect some more events outside the search region, so it's a little disconcerting if you don't know what it is and you see these spectra with some events creeping in. And this shows our search region and the heat map of where these events fall. This wasn't our thing we found, but it was Lux's, so their surprise when with their first result was radon contamination of the Teflon surfaces. And we see this as well, so we have radon daughters decaying on the Teflon surface. The S2 will lose charge, and so you get an electronic recoil event that's misreconstructed and can pollute your signal region. We see these very clearly. If we select from S1 only polonium-210, we see our Teflon walls just lighting up. And that's this plot here. What we're really worried about are these lead-210 beta decays. They can leak into our signal region, and we build a similar type of empirical model there, selecting from data, and we select as a function of radius, or we expect as a function of radius decreasing events in the inner part of the detector, and their innermost clean volume is 0. Good. So just a few slides in the upcoming result. So everything I've said now, these are all plots from our upcoming result, our new analysis. We released a result on our first 32 days of data here. So this is just the time, the calendar date since last October until February this year. Our first result was based on this exposure here. It was, the blue line is the live days. And our next result will be based on the full thing. So that's now 278 days of exposure. The boxes here are calibration times. So you see the line goes up, flattens during calibration. It's because we're only counting dark matter. Here it flattens because we had a pretty strong and rather tragic earthquake at Gran Sasso, interrupted us for a couple of weeks. And here we recovered and started taking more and more and more science data. And we've just been on a roll recently collecting good quality exposure. This will be about a ton-year exposure, spanning more than a year of operation, and the detector is still operational today. So selection conditions, you don't take we take about 20,000 triggers per hour, right? 365 days a year. And most of them are background, high energy background, a lot of them, accidental triggers, things like this. And we need a way to filter out the bad events. So we use a series of selection conditions, and here I'm going to glaze over the work of about 15 hardworking students and postdocs in one slide. and just say that we want to remove basically known backgrounds. So some examples are double scatter events. WIMPs only scatter once, so we can remove anything that scatters twice. The S2 will get wider in time versus depth due to diffusion. You can see this here, so drift time versus S2 width. There's a nice curve here, so you know things in the outlier of this might be mismatched S1 to S2. You might have your depth wrong. So you can suppress those. The signal in the top and first bottom PMTs versus where your interaction happened. So for S2, this should be constant. Interaction always happens at the gate. The S1, it depends on depth, and XY also. So we put conditions on all of these, and in the end, we cut out about 7% of events in our energy region that we say are not so good. The biggest condition is actually the fiducial volume. So as I said before, xenon absorbs a lot of radiation. And we can see here R squared versus Z in the detector. This is the detector wall, this is the top gate, bottom cathode. And for science run 1, we took this kind of blue square. We've improved our analysis enough that for this science run, for this data set that we're doing, we'll take this even larger volume, and we added a few hundred kilograms. So this is a good result of a lot of people working hard for a year on it. Good. So what this looks like in the end, so we have, remember this plot with the blue and red at the beginning where we showed the nuclear and electronic recoils. This is the 2016 and 2017 data. At the top are the electronic recoils, right on 220 calibration. You see the bands. This is actually a fit to our, the bands are a fit to our model. The black is the data. Here we have the nuclear recoil. This is americium beryllium, and here's neutron generator and americium beryllium. It's a lot cleaner, see, because it's just quicker to collect. And then here we have our background data. So for the first 32 days and for the second 247 days. What you might notice here is there's a big blue box that says blinded region. This is because we do a blind analysis. And actually, if you do a rare event search, you have to do a blind analysis. Because as I said, we take 20,000 triggers an hour. If you want to find dark matter, you'll find it in there if you really want to. And if you don't want to find dark matter, you'll cut every event away that you want to cut away. So you have to do the analysis in such a way that you don't allow yourself that kind of bias. And that's what we do. We're not allowed to look in this region until we fix the entire analysis. And after that, we don't change it. And we have enough data to fix the analysis. We have our background data outside the blinded region, all our calibration data. We could study, we have Monte Carlo data. We study a lot of the detector without looking in here. And in the end, we look in and see if the detector actually found anything we would call compatible with dark matter. We have a second line of defense. We also salted the data. That means that we have fake signal events added to the signal region. Maybe, we don't know. As an analyst, I don't know. Only a couple people in the collaboration know. And after we unblind, we will, of course, investigate these events. If they're obvious background we missed, we would cut them away. But having fake signal events in there prevents bias in this too, that we can't just cut everything away. We would know we biased ourselves if we cut these signal events. And the data is being unblinded order of days. So you can expect a result out of this data set in order of weeks. Good. So just the last couple slides now, how we parameterize these band plots in the end. So our signal and background, we parameterize in the end in S1, S2, and radial space. For the WIMP signal, electronic recoil background, nuclear recoil background, we use simulations where the physical parameters are fit simulations that aren't fixed are fit to calibration data. And this works quite well, so we get a model that models really our actual detector response with all our biases for reconstruction, all our efficiencies, and what should actually come out in the end. What we see here is our model in S1 space, which is the blue line is the total model, the black points are data, and this is fit to americium beryllium data, and then we can break it up into single scatter red, multiple scatter component, electronic recoil component. So it becomes a little more apparent if you take slices in S1 and look at the S2, you see the shape follows very well, and we even describe this electronic recoil background that's in our neutron calibration, our americium beryllium calibration naturally. A couple of the backgrounds, so surface background, accidental coincidence, I said are empirical, so we don't have a physical model for those, we fit them from data, and they're all in three-dimensional space. This is new for this result. We used to just do the 2 energy dimensions. So we don't do an actual box analysis like many years ago, but we interpret our results using a profile likelihood method in this space. And what we get for our sensitivity, and this is a preliminary projection. Actually, I think it got slightly better recently, but it's a log plot, so probably you can't tell. Our new result should have a sensitivity for these 3 mass points like this. We only computed these 3 mass points so far. We'll do the full sensitivity projection right before unblinding with the very final models. That puts us below the XENON 1-ton sensitivity. Lux, the Panda X, is also here. So we should be able to improve on our current result. And it's worth saying that we do have some discovery potential at 3 sigma. So if a WIMP at 50 GeV had the XENON 1-ton limit as its cross-section, we'd have a 50% chance of detecting it at 3 sigma. So this is actually exciting to unblind. And XENON N-ton, so the projection is down here, this will be another order of magnitude sensitivity. Great, so that's the last slide already. So please stay tuned to us. We tweet on Twitter, so we'll tweet our result when it comes out. We've got a blog. I think we tweet our blog entries probably too, so you can read all about the result, and there's been some like PR stuff to build up to it there. So interesting stuff there. You can also contact us, of course, or via Twitter or the blog, or retweet, or whatever they do on Twitter. And I should also say that this exposure will not just allow this one result. Of course, everyone's interested in this one result first order, but we can also search for a lot of other channels, low mass WIMPs, electronic recoil searches, annual modulation of the background rate, and more. So you should stay tuned to this data set. There'll be a lot of nice papers coming out of it. Hopefully not just limits, but we'll see. And our next upgrade, XENON N-ton, is moving forward very aggressively, and we should see it in 1.5 years. So thanks.
Thank you very much, Daniel. It was a very, very, very nice webinar, very nice talk. So we can start to make maybe, I mean, for the people that are watching this streaming, please, you can, in the YouTube page, you can see that there is a chat box, and you can write your question for Daniel. So for the moment, we are going to start first with the question for the people that is here in the Hangout. And okay, so who wants to start to asking about dark matter and xenon? Please, the people that is here that unmute us. Yeah, Camilo, please. No, you mute yourself, Camilo. Now you're unmuted. Okay. Yeah, we can't hear you, Camilo. I don't know if your microphone is working. No, we can't hear you. Maybe you can try to type your question, and I can ask it to Daniel. So for the moment, I have a question for the moment, because it was very interesting. I mean, one of the stuff that you were commenting about xenon is this, how you use neural network and this technique to try to pinpoint from where the electron is coming in the electron when they are drifting in the vertical axis.
Yep.
I mean, my question is related. Is expected that this spread is energy dependent? I mean, low energy electron spread more in the vertical axis. I mean, with respect with the event in where is the production event of these electrons? So how far are these I mean, this spread depends on how deep is the event happens, and the energy of the electrons, and how you manage to really trust in this training that you do to the neural network to pinpoint the. I mean, it's related also with
You're asking about the energy dependence.
Yeah, exactly. So you expect that higher energy electrons are more narrow in the spread, and the lower in the drift.
Right? It's how many electrons you have. That's the point. If you have more electrons, you have a larger electron cloud. The spread doesn't matter too much because they all arrive in XY at about the same spot. So they'll spread more in Z than they will in XY with depth. So at high energy, you get a lot of photons, you get a lot of information. In general, we have a very good resolution. So our position resolution is about a centimeter, maybe a bit more over a broad range of higher energies, right? And our PMT size is 7.5 centimeter diameter. So we achieve a much better resolution than our PMT size. At low energies, so just a few electrons, you have less information. So you have to build your inference based on just less data. And of course, the resolution gets worse there. Asymptotically at 0, it will get to 0. But it's still a couple centimeters, I think, at the lower energies we're looking at. And we verify this by looking at, for example, Krypton 83M. As I said, they have these two decays. You have this 9 and 31 keV. And a lot of times you'll combine the two S2s because they happen too close together in time, we can't separate them. But there's other times where we can separate them. So we see there's this 125 nanosecond lifetime holds on long enough, and we actually get a few lifetimes until the second reaction comes. We separate the two S2 peaks, and then we can see, basically we have two S2s that we know come from the same spot in data, and we can measure what our position resolution is between the two. And so we use this to quantify our errors at lower energy. So this is how we study it. This is why we trust the Monte Carlo simulations, right? Because we don't trust them because we verify it with data. So we know that the Monte Carlo works because we checked also in the data that it's working well.
Okay, thanks. So now Camilo, he wrote the question. I'm gonna tell to you this. He's asking if you can comment about the impact of xenon 1-ton measurement on the self-interacting dark matter, or if you have a, because he's commenting about because last week there was a paper about discussing this type of impact, but in the case of Panda X. I don't know if you...
I actually can't say, so off the top of my head.
Yeah, and in the sense he asks if you can comment or you have any information about the case of self-interacting dark matter in the context of xenon 1-ton, because there were last week there was a paper about this type of dark matter models in the case of Panda X. Okay. So I mean, it depends if you. I
didn't read it, so I actually can't say at the moment. Sorry.
Okay. Yeah, don't worry. So we have, I don't know if somebody has a question, but here we have a question in the YouTube chat from Arnie Van Das. He's asking, does xenon have any analysis for relatively strong interacting dark matter where a very large cross-section cannot be ruled out? I mean, an analysis beyond the standard WIMP vanilla scenario.
Yeah, strongly. So by strong, I guess you mean like a high cross-section.
Yeah.
I'm not sure how we would actually do that, because if it had a high cross-section, it probably wouldn't get all the way to our detector, right? It depends on how high. So yeah, if there was something going on in our detector with a high cross-section, we would see it, right? We would see a high rate, and we would immediately see it. If it had too high a cross-section, I guess it would be absorbed on the way in, so we wouldn't see it. So I don't know. I don't know if that answers the question. So we don't do a specific analysis for it, but if there was something going on in the detector that was causing a lot of events, we try to characterize everything we see. So I think we would notice it. Really, yeah. Like our background rates are really very low, right? So in this search region, it's less than an event. It's maybe an event per day or two. So.
Okay. Yes. So I guess anyone can comment in the chat if he want to more details, something like that. But for the moment, we can pass to another question. I don't know. Somebody else here in the Hangout want to ask? To unmute himself. Anyway, yeah, I also have some question, but it's more if you can go to your slides. So I'm gonna ask you to go to share screen again.
Okay. Which slide?
Yeah, in the first is in the slide 17.
That's one.
Yeah, in the plot that you have in the right, in the upper right.
Yep.
Which is the line that corresponds to the case of xenon 1-ton, or the extended? I mean, is around the case of Panda, or? So
I guess that's left up to inference. So it would be, I think, if you see my mouse, it would be somewhere here.
Even lower than Panda. Okay.
So what I can say is that so here it starts to flatten out our event rate, and it remains flat throughout the science run. We don't like to show the plot yet because we're going to use that data for annual modulation studies. So you could infer from how flat it is something like a limit on annual modulation. So that's why we don't show the plot over the whole science run, but I can tell you at least that it remains flattish.
Okay, it's around there. Okay. Yeah. I mean, if there are kind of ongoing research in that part, better not to. Yeah. So yeah, and then in the slide 21, you show the progress of XENON that is impressive. How it's taking data with the time. So you said that in the next year it's expected to make the upgrade to XENONt?
Yeah. So this is kind of a rolling process, right? So we're already started designing, screening, ordering components for XENONt, even constructing parts. We want to run XENON as long as possible. And depending on what this result does, it will kind of depend. So if we find really a signal for dark matter that we think is significant at all, we'll probably extend the science run of XENON. But the plan now is to keep running XENON. At some point, its duties will kind of switch towards prototyping and tests for XENONnT, because there's no better place to test new things than on a perfectly running detector. And once the XENONnT has reached a certain stage that we actually need to take this cryostat apart and put it in, then we'll do that. So we're going to run XENON, of course, as long as we can and collect all this very nice data we're doing. And then kind of at the last minute, when XENONnT is staged and ready and getting to be built in Gran Sasso, then we will stop the operation and make the switch. So the time was, I don't know, I can't say for sure when XENON will stop, but the XENONnT should be running in 1.5 years. I think you can assume XENON has to stop this year sometime.
Yeah.
If we can hit that schedule.
So in principle, we could extrapolate this straight line to 1.5 years, more or less.
Yeah, but I mean, the exposure may or may not get so much better, right? So at some point you need a bigger detector because you become background limited and your sensitivity doesn't scale linearly anymore with your exposure. So I guess after science run 1 is when we really, or sorry, I keep using collaboration slang. After the science run is when we will really kind of do some discussions on how long we're going to run this thing. And probably it doesn't make sense to run it for many, many years. Just the extra 6 months or a year is enough.
Okay. Yeah, understand. So in a little bit regarding with this, the same. So I mean, XENON is expected to, for instance, to have new results, for instance, in this summer, like to upgrade what was presented during this week, like last week or something like that. Or
there were no results presented last week, right?
No, there were some in a conference. I mean, I was following how was happening in Twitter, so
yeah, okay.
Last week there were some movement about XENON talks.
Yeah, for XENON, I mean, I think so. The last week was this UCLA Dark Matter conference. I think they basically showed this. This is just our projected sensitivity. It's not a result. It's not a limit even. There could still be dark matter. Like we still have a chance of finding dark matter with this. But this will be the result that comes out in I guess March is our target right now. So end of March for the paper. Don't hold me to that though, but it could be a plus or minus. But that's the order of time, so early spring. And then I guess you can expect over the next year, maybe the earliest ones in summer or a bit later, kind of some of these alternate models like axion searches, and annual modulations, and things like this, papers to be coming out based on this one really high quality data set we've taken.
Oh, cool. So I don't know if somebody has a question, please unmute and ask because I could continue. So, but in that plot that you showed with this current level of XENON, it's not possible yet to see to start to observe the neutrino floor.
No, I mean,
it's still too far.
Right? So at least we assume we're just missing it. XENONnT, this becomes then a thing. The sensitivity will kind of go through this neutrino limit, so we expect to see a signal from these boron-8 neutrinos and in XENONnT.
Okay, so yeah, okay, we have Arnivan Das, the guy that asked before. He commented a little bit on his question. Was was the case when dark matter can scatter with the shielding, this type of models. So it's more than interact much more than the typical WIMP, but not inside the figure shuffle. It's in the shielding itself.
So I guess in this case, the dark, well, I don't know. I've never really heard of a model like this, but I guess in this case, the dark matter would have to be somehow weakly interacting enough to make it through the mountain, and strong enough to scatter with
the shielding. Yeah.
So I don't know. I mean, if it made a nuclear recoil, I guess we'd still see it in the detector. So this we would for sure still see.
Mm-hmm. So I don't know, the people here in the Hangout, do you have questions for Daniel? So I guess no. I mean, for me, I mean, I could continue making questions, but it's better if somebody else could ask. But if not, I guess has been a very, very nice webinar. In fact, this is very, very nice, especially all the information that you during the whole webinar is very interesting, especially for people interested in dark matter and direct detection, and also for the theoreticians that they will bring many models to try to see what the exclusion of their models in XENON. So first of all, we have to thank Daniel for this webinar. It was very nice. And second, for all the people that is following the webinars, or if it is your first time in this watching this type of research seminars in YouTube, so please, you can consider to subscribe to the YouTube channel. It's a very nice experience for us, and also for all the people that cannot attend to conference to follow in what is happening in a specific research topic given by the same researchers. And if you have PhD students or people interested in this, please spread the word, and let's try to make this more affordable for all the people. So Daniel, thank you very much for your webinar again. And for all the rest of the people, see you in the next time. This was the end of the season 6. We finished with a very nice talk. Next, in 2 weeks, we're going to have another webinar. We're going to start the season 7. That is going to be, if I remember well, Olsir Sumenansari from ENF and Padova. And also in the next season in the law physics, just to announce it, also we're going to introduce other type of webinars, but this time is going to be, we're going to start to make colloquiums. So we're going to enlarge our topics, and we're going to try to make it more affordable for all the fields in physics. So thank you, everybody, and see you in the next time.